Hi everyone, I'm Debasatham and you're watching EE635 Applied Linear Algebra. Welcome to module number 2 of the second lecture. So we have been looking at how to solve linear systems of equations, and what we have found out is something about equations, something about equivalent systems of equations. Right? Now, we'll see what we can do with these equivalent systems of equations. Also, more importantly, how do we get these equivalent systems of equations? Okay, so let me share my screen. Right, it should be visible to you any minute. Yeah, this is visible. So let me go to the whiteboard. Okay, so let me quickly recall what equivalent systems are. So two systems of equations, ax equal to b, which is system 1, and a hat x equals b hat, which is system number 2. Let me remind you again that a and a hat, b hat, they need not have same sizes. Now, of course, b has to be a vector, b hat has to be a vector, but the sizes can be different. A hat must have same number of columns, but the number of rows may be different. Right? So these two systems are said to be equivalent to each other if system 1, every equation in system 1 is a linear combination of equations in system 2, and every equation in system 2 is a linear combination of equations in system 1. If that is so, then the two systems are going to be called equivalent to each other. And we have seen our first theorem of this course said that equivalent systems will always have exactly the same set of solutions. Now the question is, the all important question here now is that how do you get equivalent systems of equations? All good. Then you have one system of equations, and then you obtain new equations by looking at these linear combinations. But where is the guarantee that you should be able to write down the original equations also as a linear combination of the new equations? Yeah, is the question clear? I have a system of equations that is the given problem to me, ax equal to b. I want to solve it. The idea is to convert them into an equivalent system which is easier to solve. What we mean by easier to solve is something that needs to be defined. That we'll see very soon. Yeah? In fact, most likely in the next module, we'll see what we mean by next module. We'll be able to see what we mean by equations that are easier to solve, simpler to solve. But then, how do we get equivalent systems? Right? Otherwise, there is always this doubt, right? For example, suppose I have ax equal to b, but then I do various linear combinations, and I obtain a hat x equals b hat by taking linear combination. This suppose has solution set S1, and this suppose has solution set S2. Then by the fact that these equations have been obtained from this one, that proves that S1 will be contained in S2. But it may so happen that S2 is strictly bigger, right? S2 may have lot of more solutions, lot of extra vectors in it, which are not in S1, right? But we want exact same solution set. So I want equivalent system. Just obtaining new equations is not enough. I want to obtain new equations, all right, new easier equations, but at the same time, I don't want to change the solution set. So I want equivalent. How do I get that? So this is the all important question. So let me write this down. The important question that we would like to answer in this module or later, that how do we obtain equivalent systems of equations? Of course, before we obtain, one might even want to ask, how do I even check whether two systems are equivalent or not? Yeah, that is also an important question. Before we devise a method to obtain equivalent systems, I should be able to first discern whether this is indeed equivalent or not. It turns out that answering this question, that whether how to discern whether two systems are equivalent or not, uh, actually will give us a method of obtaining obtaining equivalent systems. Let us see. The trick will be to have some observations. Yeah, in fact, 3 observations will finally lead us to this, lead us through this problem of obtaining equivalent systems, or at least discerning equivalent systems. First observation is the following. When I write down an equation, a11x1 plus a12x2 plus dot 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 up to a1nxn equals b1, by matrix vector notation, this is nothing but this row vector multiplying this column vector equal to the scalar. Yeah, this is observation number 1, which then means that when I have a linear combination of the type a1 alpha 1 into a11 x1 plus dot 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 into into a1n xn plus alpha 2 a21 x1 plus dot 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 a2n xn plus alpha m a m1 x1 plus dot 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 a mn xn equal to alpha 1 b1 plus dot 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 up to alpha m bm. This, when I write this in the matrix vector notation, will come out to be something like this: alpha 1, then a11 dot 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 to a1n, this row vector, plus alpha 2 into row vector a21 a2n plus dot 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 plus alpha m a m1 a mn. This linear combination of the rows is equal to the linear combination of these entries. Does this make sense? Okay. Oh, sorry, I missed something in here. Hang on, I'll correct it. Right. This, of course, this is a row vector. This row vector multiplies x1 up to xn, the column vector. This is equal to alpha 1 d1 plus dot 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 up to alpha n dn. Does this make sense? So this is a linear combination of rows. You see, linear combination of rows and linear combination of columns is something I'm sure you have already seen before. Yeah. So given some row vectors, say 1, 2, 3, and 4, 5, 6, and 7, 8, 9. I have 3 row vectors. I can look at this linear combination, right? I can look at 2 into 1, 2, 3 plus 3 into 4, 5, 6 plus 8 into 7, 8, 9. Yeah, what is this result? This result is, of course, this is 2, 4, 6 plus 12, 15, 18 plus 56, 64, 72. And, oops. And of course, the result is, the result is, this is 2 plus 12, 14 plus 56 happens to be 70. This is 4 plus 15, 19. 19 plus 64 is 83. Then 6 plus 18 is 24. 24 times 72 is 96. This is a linear combination of rows. But likewise, you have a linear combination of rows here. Yeah. Okay. So what this tells us is that when we are looking at linear combination of equations, each equation corresponds to a row vector, right? Looking at linear combination of equations is the same as looking at linear combination of rows. Yeah, that's it. And looking at an equivalent linear combination of the right hand side, which is just a vector, right? Now, this is where observation 1 ends, and of course, observation 2 starts. Observation 2 is going to be very important for us. It's in fact going to be such that it's going to be used again and again throughout this course. And that is why I'm going to do it in a general manner. What this observation 2 tells us is the following. When I have, say, row vectors like a11, a12, dot, 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 up to a1n, this is a row vector. I have another row vector a21, a22, dot, 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 up to a2n, and I have m such row vectors am1, am2, dot, 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 up to amn, and then I look at their linear combinations. Okay, so I'm looking at alpha 1 plus alpha 2 like this. Yeah, notice that this is nothing but, I can rewrite this as row vector alpha 1, alpha 2, dot, 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 alpha m. Notice I had alpha 1, alpha 2 as just real numbers so far. Now I'm writing them down as a row vector. This, when multiplies a11, a12, dot, 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 up to a1n, a21, a22, dot, 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 up to a2n, am1, am2, dot, 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 up to amn, this matrix. So this row vector times this matrix is nothing but this linear combination. Go and check. This is true. So linear combination of rows is nothing but left multiplication by a row vector to a matrix. So this left multiplication by a row vector to a matrix is nothing but linear combination of the rows of the matrix. Okay. Similarly, as will be important for us later on, if I have, say, column vectors a11, a21, up to am1, and then a12, a22, a22 up to am2, then dot 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 a1n, a2n, dot dot amn. So these are column vectors, right? Suppose I have linear combination of these columns, beta 1 times this plus beta 2 times this plus dot 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 plus beta n times this. There are n columns now. Yeah, this linear combination is nothing but a11, a12, dot 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 a1n, a21, a22, dot dot up to a2n, am1, am2, amn, multiplying this column now, b1, b2, dot 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 up to beta n. So linear combination of columns is nothing but right multiplication by a column or matrix. Yeah, just go ahead and check. This is what it is. Okay, so let me write this down. Linear combination of rows of a matrix is equivalent to left multiplication by a row vector. In fact, the row vector is that of the coefficients. And linear combination of columns of a matrix is equivalent to right multiplication by a column vector of the coefficients. This is our observation number 2. And then this leads us to observation number 3, which is the following. So when I have Ax equal to B, a system of equations, suppose from here, by taking linear combinations, I have obtained A hat x equals B hat, where A hat belongs to a matrix M hat n, and B hat has M hat number of entries. And this actually means there exists a matrix M, which is of size M hat cross M, such that A hat is equal to M hat times A and B hat is equal to M hat times B. This immediately follows from observation number 3. Yeah, let me give you some time to see that this is true. Okay, because just see how is A hat obtained. Every equation in A hat is a linear combination of equations in A. So that means for every equation there in A hat x equals B hat, that is for every row of A hat, there exists a row vector that multiplies A from the left and gives me that row in A hat. Yeah. So now I just collect those rows together and form this matrix M. Then M times A will give me A hat. Right? That's it. Now, so then how do I get equivalent systems of equations? So one way of getting equivalent systems of equations guaranteed is the following. That suppose, so these observations end, this is new claim that I'm making. Suppose M, oh, I wrote M hat, I should not have. These are not, they're not hats. Yeah, that's it. This is correct. Yeah. So what I was saying is, suppose M happens to be a square matrix and invertible. That means its determinant is non-zero. Yeah, in that case, I have A hat equals MA and B hat equals MB. But then this also means A is equal to M inverse A hat and B equals M inverse B hat, which means not only is A hat X equals B hat obtainable from AX equal to B, so is true for AX equal to B is also obtainable from A hat X equals B hat, which means two systems are equivalent. So one way of getting equivalent systems is to obtain linear combinations of the rows such that the corresponding matrix M is invertible. That will give you, that will give us equivalent systems, right? Okay, so think about this, and then we meet for the next module. To help you think about this, look at this immediate attention. Find out the matrix M that converts system 1 to system 2. Yeah, in our immediate attention 1 problem. Is M invertible here? Is this M unique? Think about this. Homework 2 is this one. Yeah, given two vectors U and V, write them down as a linear combination. U and V, write their linear combination. So given another vector W, write W as a linear combination of U and V and see whether it is possible or not. Then rewrite your answer as AX equal to B form, and then try and construct a W hat such that W hat cannot be written as a linear combination of U and V. Okay. And then we have homework number 3. Give an example of 3 vectors U, V, W in R4 such that non-trivial linear combination of them is 0. Write your answer as AX equal to B. Find another non-trivial linear combination U, V, W that results in this MC. Okay, try this. Homework 2 and homework 3, you can think about them after you have finished all the video lectures for this week. But finish immediate attention number 2 first, and then proceed to module number 3 of this lecture number 2. Okay, till then, take care. Let's meet for module number 3.